Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. Here we have the subject that is theory of computation. Let me start with what we had in the previous episode. Actually, we have seen the context free languages, the context free grammar, and what is the language recognized by the context free grammar, then how the language or the set of all strings are recognized by the context free grammar with the help of the derivations. So, those things we had seen as far as the previous episode is concerned. As far as this episode is concerned, we are having that is the definition for parse tree and how that is a parse tree is constructed given a grammar as well as a string which is part of the language of the grammar. Then followed by that we are having that is ambiguous grammar, that is when we call a grammar is ambiguous, and then we are having that is the elimination of the ambiguity of a grammar. Suppose if the given grammar is ambiguous, how do you come up with a grammar which is equivalent for that, but at the same time it is unambiguous? These are the things we are going to cover as far as this episode is concerned. Let me start with the definition for parse tree. First of all, parse tree is going to be a pictorial or a diagrammatical representation for the derivations. So, what we wanted to do is given a string, from that actually we will be given a grammar. From the grammar, how do you find out whether a string is accepted by the grammar or not? That is, whether a string is there in the language of the grammar or not. One way of evaluation is just making use of the derivations, where we start from the starting symbol of the grammar. In each step of the derivation, we will expand one variable from the grammar replaced by the appropriate right hand side required for getting the string. And finally, we will get a sentential form which contains exclusively string of symbols. So, the other way of describing or evaluating whether a string is there in the language of the grammar is by using the pictorial representation. We call it as the parse tree. So, as far as trees are concerned, there will be a root and there will be some number of internal nodes and some number of that is leaf nodes. As far as a parse tree is concerned, all these nodes, that is whether it is going to be the root node or the internal nodes or the leaf nodes, they are all supposed to be labeled. So, the labels available in various nodes are the symbols available in the given grammar. So, what is supposed to be in the root and what should be on the internal nodes and what should be on the leaf nodes. As far as the root node is concerned, we will be having only the start symbol of the grammar. So, the start symbol will tell you that is what should be on the root. It is true for all kind of parse trees. Then as far as interior nodes are concerned, they are all labeled by the component called that is variables. So, every internal node in the tree must have a variable as its label. Then what we will be having as far as the leaf nodes are concerned. So, the leaf nodes must be labeled by the terminals given in the grammar, or it can even be epsilon also. Epsilon is not part of the there is a grammar symbol. So, it is required to specify whether epsilon can be in the leaf node of the tree or not. So, now the question is how do you define the relationship? Relationship I mean that is from the parent node, how do you find out the derivation or how do you find out the derive the child nodes? So, here we will make use of the various production rules available in the grammar. If there is a need for expanding a node by inheriting the child node of that particular node, the node in question must have a label from the variable set. So, if there is a variable available in the grammar, there will be definitely one or more number of rules available for the grammar. So, then if a variable is to be expanded, we will replace it by the production rule, that is one of the production rule available for that particular variable. Suppose if the production rule has two number of symbols available on the right hand side, then the variable or the node with that variable is to be expanded, or we will go for one more level by producing its child node with labels from the right hand side of the production rule. So, if A is a node for which there are two number of child nodes, maybe n1 and n2, these n1 and n2 nodes must have the labels which are available on the right hand side of the production rule for A. So, if there is a subtree available with A as the root node, n1 and n2 as the child node, then there should be a production with A as the left hand side and the label for n1 and the label for n2 as the right hand side. Then only we can say that the parse tree is going to be a valid parse tree as far as the given grammar is concerned. So, the relationship is given here. If an interior node is labeled A and its children are labeled with x1, x2 up to xk, as far as A is concerned, we have the notational convention that it should be a variable always, but whereas on the child nodes are concerned, it can be either a variable or even a terminal. That is what the convention x1, x2 etc. up to xk are used. If the root node or the interior node is having a label A and its child node are having the label x1 to xk, then it is strictly required to have a production in the grammar that A derives x1, x2, x3 etc. up to xk. So, if this production rule is available, we can have a subtree of that kind, or if you have a subtree of that kind, then definitely there should be a production available for that in that grammar in this form. So, this is what the definition given for the parse tree. First of all, you should know what should be on the root of the parse tree, then what should be on the leaf nodes of the parse tree, and what will be there on the interior nodes. Root node is always required to have the start symbol of the grammar. The leaf nodes must have only the terminal symbols from the grammar which are actually used for generating the strings. Then interior nodes we can have any number of variables. Now, let us see one simple example, that is how we are constructing the parse tree from the given grammar. Here we are considering the very familiar grammar, that is an expression grammar. E derives, the first alternate for A is E plus E, and the second one is E star E, the third one is opening bracket E closing bracket, where opening bracket and closing bracket are the terminals, and the last alternate for the grammar is going to be production rule is ID. Suppose if the string which we want to derive is ID plus ID star ID, now the question is how do you, that is, construct a parse tree for this? As far as this grammar is concerned, we have only one variable and that variable is to be considered as the start symbol of the grammar. So, it is going to be E. So, that is a symbol available on the root of the parse tree. So, here we have the label E. The next is we are having actually 4 options for the expansion of E. So, the string which we have to derive is going to be the very important factor that will decide on which course of or which kind of alternates can be applied for this parse tree. So, here we have a string that is ID plus ID star ID. So, we find that when you are scanning from left to right, the first operator we are having is going to be plus. So, it is better to go for E plus E as the expansion for E. So, I go for, that is, expanding this E by E plus E. So, the children of this E are, first one is E, the second one is plus, and third one is E. We are getting these 3 as the child nodes only because of we have a production E derives E plus E. When you are looking at the child node, it is plus is a node which is considered as the leaf node because of the label available on that node is plus, which is a terminal. So, there is no further expansion for this node, but whereas we can't leave this E and this E as it is. So, there is a need for expanding these 2 E's. So, now the first E when you are considering, it could be expanded using ID because of next there is left, on the left of plus we want to have only an ID, that is a person operator operand. So, it is E is expanded by ID, then the next one to be expanded is the second E. So, we want to still generate an expression with multiplication as the operator, but multiplication is so far not generated. So, the right choice for expanding this E is now with the help of an expression multiplied by another expression. That is the second production rule which is given for E, that is E star E. So, E star E is going to be the expansion for E. Once again, if you look at the child nodes, E is a variable, star is a terminal, and E is another variable. So, star it is not further required to expand, but whereas in the case of the first E and the second E, we have to expand them, and if you go for the first or second or even third alternate for this E, it will go for a string which is more than what we wanted to derive. But at the same time, if we expand this E by ID and the second one by ID, we will be left with a tree where all the branches are explored till terminals. So, whatever the path we are taking from the start symbol of the grammar, they all will tend to reach terminal whatever be the path is. So, here if you take the first path, it is going to be ID, the second one it is plus, the third one it is going to be once again ID, the fourth one is multiplication, that is also a terminal, and final one is going to be ID, once again it is a terminal. So, now all the terminal nodes here are labeled in yellow color, and they are actually having the label ID plus ID star ID. So, if you say that this is going to be the correct parse tree for the given sentence, then when you are collecting all the leaf nodes from the tree, from the parse tree, you should get exactly the same string what we want to recognize. It should not be less than what the string we want to recognize, or it is not like more than that. Exactly whatever the string we want to generate, it must be there when you are collecting all the leaf nodes available in the parse tree. Then we can say that that is going to be the correct parse tree for the given sentence. Also we can declare that the string is there in the language of the grammar which is given for us. So, that is what that is how the parse tree is constructed from the given grammar for a particular string. So, as far as this example is concerned, it is going to be very simple, but when you are having a very large string, then every time it is required to make a choice about what should be the right production to be used for deriving the string or not. So, if the productions are not appropriately chosen, even for a valid string, sometimes we may not be able to find out the correct parse tree. So, on those kind of situations, it is required to do some kind of backtracking by deleting some of the branches which we have already generated, and then selecting the right rule, we will be able to find out that. The point is, if the string is there in the language, definitely we will be able to construct a parse tree in a successful manner. At the same time, if the string is not there in the language, definitely we will fail to find out a parse tree for that string. So, that is how the strings are validated or strings are derived from the start symbol of the grammar using the grammar and represented with the help of the parse tree. The next one is ambiguous grammar. So, the meaning is, can we have more than one parse tree for the given sentence? So, we have seen that just a context free grammar, and there may be some number of strings available in the language or even infinite number of strings available in the language, and also we have seen that derivations are there for the strings available in the grammar, language of the grammar, and even parse trees are available. As far as derivations are concerned, it can either be leftmost or the rightmost, but whereas in the parse trees are concerned, we will be having only one way of representing the derivations. It is not whether it is going to be leftmost derivation we are following or the rightmost derivation we are following, there is only one way of representing them in the case of pictorial representation or parse tree representation. So, now the question is, suppose if the string or if you are given a string, whether we have more than one parse tree for the same string or not. If we can construct more than one parse tree for the same string, then the string is called an ambiguous string, because if there is only one parse tree or at most only one parse tree, there is always a deterministic behavior from the parsing action, that is in the derivation. Every time we will be left with only one appropriate or only one choice. So, we can straight away go for expanding that without any ambiguity. Finally, we will definitely reach the string which we want to recognize. But if you find that there are more number of parse trees, then every time we will be left with more than one choice. So, if we have more than one choice in a particular period, that is period of expansion, then if it is two number of choices, then either we can go ahead with the first one or even we can go ahead with the second one. The first one may give you a parse tree, the second one will give you different parse tree. That is, as long as the expansion or the production rules used for expansion are differing, there will be a different parse tree we will get as output. So, if the string is ambiguous, then the parse tree what we are getting as output will also be different. So, if the grammar gives us more than one parse tree for any particular string, then the grammar is also called an ambiguous grammar. So, if the string has more than one parse tree, then we will be calling it as ambiguous sentence, and if the grammar has more than one parse tree for any sentence, the grammar is called an ambiguous grammar. Let us go for a break. After a short break, we will continue the lecture. Welcome back. We have just seen what is an ambiguous grammar. So, here is a definition available for us. A grammar G with the usual components, 4 components. V is there, that is a variable set, terminal set, then productions, then start symbol of the grammar, which is said to be ambiguous if there is at least one string. So, we can't say that always for every string there will be more than one parse tree. If you find that at least one string, that is W, in the terminal star, that is the closure of the terminal set, for which if there is two different parse trees, I mean there is more than one parse tree if it is existing, then the grammar will be immediately called an ambiguous grammar. So, now we have some examples for the ambiguous grammars. So, once again we are considering the very familiar grammar that is called the expression grammar. E is E plus E, or E can be even E star E, or open E close, or even ID. The string what we have considered here is once again the same string, it is ID plus ID star ID. So, now we have two number of parse trees. Let us look at the first one. So, the start symbol of the grammar is going to be E in both the trees, because we have only one variable, that will be the start symbol of the grammar. So, the first E is expanded by using E plus E, but even if you go for expanding the root by E star E, we find it is going to be valid. So, here in the second tree we are expanding this E by E star E, whereas in the first one we are expanding this with E plus E. So, there itself we find that these trees are different, or these two trees are different, because the first one we have the first level child plus, and the second tree we have a star. Once again, if you go for the third level of the parse tree, so this E is supposed to be expanded only by ID, because we have no other choice. If you go for any other choice, then the desired string may not be able to be generated. So, we will be left with only one choice here, it is ID. This plus cannot be further expanded because of it is a terminal. Then this E is expanded using E multiplied by E, because that is strictly needed for us, and once again here also it is going to be E derives ID, and here also E derives ID. So, except the first expansion of this E, all the others we are forced to do so. Once again, when you are looking at the second tree, except the first expansion of the tree, that is first the expansion of the root of the parse tree, all others we are forced to do only those kind of expansions, because if you are expanding this E by any production other than this E plus E, we will not get the desired string. So, we are forced to select E plus E, this E is expanded to ID plus no further expansion due to it is going to be a terminal, and then this E is also expanded using ID, finally this E is also expanded using ID. So, if you look at these two trees, you just collect all the leaf nodes which are marked with red boxes, ID plus ID star ID. Here also same thing we are having, ID plus ID star ID, and look at the start symbol of the grammar, they are also same. So, the start symbol of the grammar is same, because every grammar should have a single start symbol. So, there is no question of having two different roots for these parse trees, they are same, and when you are collecting all the leaf nodes, they are also same. So, immediately we can say that the parse tree, or we have two different parse trees for the string, that is id plus id star id. So, the problem with these two different parse trees is, when you are looking at the first level, that is the root, when we go for expansion, we are having two different choices and both are valid. When the parsing is to be made as deterministic, this will create problem for us, because either we can go for the left one or e plus e, or you can even go for e star e. But strictly speaking, there is only one production rule that is going to be valid, and that can be identified only if you are very sure about the priority information of these kind of operators as well as associativity. So, whether plus should take the higher priority than multiplication or the reverse. Actually, we find that asterisk or the multiplication is supposed to be given higher priority. So, what is to be expanded first? It is all depending on which operator is going to take higher priority and which is taking the lower priority. So, if that information is also incorporated into the grammar, then we can very easily avoid the ambiguity available in the grammar. But as far as the expression grammar is concerned, it is very much obvious that what should be given the higher priority and what should not be given the higher priority. But this information may not be visible, there may not be very much clear as far as other programming language constructs are concerned or different grammars are concerned. So, now the question is, suppose if the given grammar is ambiguous, how do you eliminate the ambiguity available in the grammar? There are tools available, there are parser generated tools which are even capable of handling these ambiguous grammars, but those kind of parser generators will accept some additional information regarding the priority and associativity of the various operators or the terminal symbols. By providing those additional symbols, even we can construct a parser from the kind of ambiguous grammars. But if such a provision is not available in the parser constructor, then there is a need for giving grammars which are always unambiguous in nature. So, we should find out how do we eliminate these kind of ambiguities from the grammar. Actually, there is no rule available for the elimination of the ambiguities available in the grammar, or there is no algorithm available for the elimination of the ambiguity available in the grammar. The only way to eliminate the ambiguity available in the grammar is just by looking at the way in which we can rewrite that will remove the ambiguity available in the grammar. Actually, it is required to find out the reason which is causing the ambiguity of the grammar and how we can rewrite the grammar, so that the written grammar without changing the language will give you an unambiguous equivalent or unique parse tree for every string available in the language of the grammar. We shall consider one simple example. This is what your expression grammar. We have considered there one more operator, that is exponentiation. So, now this grammar, we find that the exponentiation, even before that, any expression inside the bracket will be having the highest priority out of all these list of production rules. So, that is going to be the first one here we are having, that is P is opening bracket E closing bracket, and as usual it is going to be ID, which has no other operation involved in retrieving the value of this ID or the evaluation of this expression. So, these two are given the first one, and the next operator which is taking priority, highest priority is going to be the exponentiation. So, we will be considering this, and the next one we are having is asterisk, that is considered, and the next one or the last one is going to be plus. So, now if you are writing, when you are rewriting the grammar, we have to write it from the lowest priority operator, that is plus, then it is connecting with the T connects to star, and it is connecting to F, then F is connecting exponentiation, then otherwise it is going to be P, then P connects to any expression inside the bracket. So, now if you find that you can't straight away use an expression which is having exponentiation as the operator or which is having multiplication as the operator. If you still want to have, the only way to reach that is from E you go to T, then T derives T star F, and now if you find that when you are having that is your T, so this is never going to generate any operator with the plus, because when you are expanding this T, either it is capable of generating that is once again asterisk, or it can go for F in turn can generate exponentiation. So, always we will find that the operator with the highest priority will be on the left side unless or else it is enclosed inside S bracket. So, here it is either multiplication, or it can even be expanded by using exponentiation, or it can even be expanded using this opening bracket E closing bracket. But all these are taking either higher priority or higher precedence than this asterisk available on this side. Still, if you want to get this plus on the left hand side of this asterisk, only chance is we have to go for using the expression inside the bracket, otherwise it is not possible. But whereas in the previous grammar, that is in the original grammar with ambiguity rules, on the left hand side of asterisk, it is possible to even generate an expression with plus. So, what will happen is this plus will be forced to evaluate even before the evaluation of this asterisk. So, that is the reason why the ambiguity has been created as far as this grammar is concerned. So, this is what the rewritten grammar without any ambiguity. Look at this next grammar. So, this is once again a grammar which is ambiguous, which is describing the syntax of the if statement in any language. So, it is the I stands for if condition then, S stands for the statement. The next one is if condition then a statement, else once again a statement, or it can be any statement other than the if statement. So, this is also having some problem with that is ambiguity, because of we are having the else construct. The else is here called as the dangling else. So, whether it should be associated with the nearest if statement or with the farthest. So, it can be as far as this grammar is concerned, this E can be associated with any if that is preceding that E. So, but that should not happen. So, the languages are normally resolving these kind of conflicts by associating the else with the nearest if. So, here how do you resolve that? So, we have to split up the statements into two groups, that is if statements, one with matched if statements and another one with unmatched. So, in the case of matched, if a statement is having the if along with else, that is if then and else, it will be treated as match statement, and if a statement is having only the then component but no else component, then it will be considered as unmatched statement. So, by classifying these two, a matched statement will always be matched by a single production, and an unmatched statement is always matched by another single production. So, if you are sure about the statement is a matched one, there is only one rule for that, and once again if the statement is an unmatched one, once again there is only one rule available for us. So, there will not be any ambiguity in deciding the course of production or the alternate production in order to recognize this statement, because the statement is initially known as whether it is ambiguous or unambiguous. There will be exactly one set of rules to recognize whether the statement is the given statement. The given statement, it can be even a matched statement or an unmatched statement. So, the rewritten rule is available here. We have S, which can be either a matched statement or an unmatched statement. A matched statement is the one with the then construct, that is if then construct as well as else construct, and the very important one here is both the statement components once again should be in turn matched. If they are unmatched, the total statement will become unmatched. So, there is a need for having only matched statements here, there is M here as well as M here, and if the statement is anything other than the if statement, once again that is also considered as a matched statement, because in that kind of statements we do not have a then component or even an else component, both are 0. And when you go for an unmatched statement, it is having a then construct, if then construct, but there is no else. So, it is I followed by a matched statement. For this statement we may have that is your then and else, but whereas as a whole when you are looking at this particular statement, we find only if then is there but no else. The second case, we find that if then is available, a matched statement is available, then else is available, but what follows this else is going to be an unmatched statement. So, here this is already declared as unmatched, and this E is strictly required or strictly should be associated only with this I. It is because of this M already has equal number of thens and elses. So, even though we find that I and E are involved, this E we are very sure that it must be associated only with this I, not with anything else. So, when you are looking at these three productions, the ambiguity available in the dangling else grammar has been completely eliminated. So, now the question is, can we say for all grammars, for all languages, there will be unambiguous grammar equivalent or not? So, there is reason for that. We are even having that is languages where we will be having that is the grammars always ambiguous. So, they are called inherently ambiguous grammars. So, here is the example available which we will be having, that is where the language is going to be inherently ambiguous. So, we shall go for the summary. So, we have seen the parse tree which is a pictorial representation, and then we are having the ambiguous grammars and the procedure for eliminating the ambiguity available in the grammar. So, that is about this topic. The question components, the parse tree definition, and what is the meaning of ambiguous grammar. Even we can maybe asked to write some ambiguous grammars, how we are eliminating the ambiguity available in this grammar, and what are the inherently ambiguous grammars, and the example for inherently ambiguous grammars. So, these may be the questions as far as this component is concerned. So, with this I conclude this lecture. Thank you all.